Okay, so this is going to be a little bit of a preview on circular motion and rotational motion, just to get some of the initial ideas and concepts down before you look at the chapter itself. So when we're talking about rotational physics, we have some particle, let's say, that is rotating in a circle, okay? And the circle, if we look at, or we want to find the displacement of a circle, of course, this circle will have an R, okay? And we can find the circumference of the circle by this equation, 2 pi r. Now, what happens if we wanted to take like a little slice of a pie, okay, and each one of these blue lines is equal to r, and the distance radially along this curve, we're going to call this delta S. Okay. So we have a couple things we have going on. We have translation of displacement, and this delta S would be something that would be equal to in meters, or have a unit of meters. Also too, while an object or a particle is rotating, we'll say it's massless right now, it's rotating, and we're going to say it's rotating in this direction right here. We also have angular displacement. Okay, and what is angular displacement? Basically, it is, if you will, the amount of degrees it moves. In this case, we're going to talk about rads. Now let's go back to the circumference equation here. We have 2 pi r. Our 2 pi basically is radians. 2 pi is approximately equal to 6.28 rad. Okay, so we're going to transition this equation into something we can work with for angular displacement. So let's take a look at this equation, and we have, let's look at the slice of pie we have here. We have a delta S. We also have an R. And then we also have this angular displacement that we're moving from a certain beginning position to an ending position. So that 2 pi is going to translate to our delta theta. So 2 pi, we're going to call that delta theta. And then we have the R. So let's compare. C equals 2 pi r. The C now becomes delta S equals 2 pi, which is delta theta, and then of course R. And so this is one of our circular motion equations, where the arc length is equal to the angular displacement times the radius of the circle. Okay, so let's look at another concept, and this is going to be talking about angular velocity, because as we are rotating around at a certain speed, there's a couple things happening. There is velocity of the wheel, which is in meters per second, and there is also angular velocity. So we need to equate those two things. So what we can do is that we'll take this equation right here, delta S equals delta theta R, and we'll divide both sides by delta T. Okay. And what we get is that we have displacement divided by delta T. That is equal to just plain velocity. Okay, then we have this equation right here, or this term right here. Let's leave the R out for now. Delta theta over delta T. This right here is our angular velocity. Okay, so for right now, I'm just going to put this in like this. Our angular velocity times the radius of the circle that the object is rotating around. Now, the delta theta over delta T is also called angular velocity. And we represent angular velocity with a Greek letter called omega. Kind of looks like a little W. And that's equal to the change in angle over the change in time. So let's go to this equation up here and write it out with the omega sign. So V is equal to omega R. We can also write this as omega is equal to velocity divided by the radius. And so these two equations you'll be using a lot when you are transitioning from velocity to angular velocity. Okay, so now let's look at one more concept, and that is with acceleration. So let's start off with what we have. We have delta S is equal to delta theta R. So this is our displacement. And then we have delta V is equal to delta omega times R. We also, this is our velocity. And then we have to look at one more thing, and this is with acceleration. Now I'm going to write over here on this side what this looks like. You may see it this way as S equals delta theta over R. Actually, it should be delta S. Velocity, a lot of times, is just written V equals omega R. Okay, now we're going to look at acceleration. So let's take our velocity equation. V equals delta omega. And we're just going to make an assumption that our V is a delta, is equal to delta omega R. And we're going to do the same thing. We're going to divide both sides of the equation by delta T. Okay, now that we did that, let's take a look at what we got. We have over here, and I'm going to make this a delta just for so we don't get mixed up. Delta V over delta T, that is just simply acceleration. Okay. And then we have delta omega over delta T. So let's write that down, delta omega over delta T. And then we have R, the radius of the rotation. Now this delta omega over delta T is angular acceleration. And we identify it with the Greek letter alpha, which looks something like that. So that is our angular acceleration. So we can put over here that acceleration is equal to the angular acceleration times r. So here we have our three conversion equations. And let's just talk about translational velocity and acceleration a little bit, and tangential acceleration and velocity. So if we have a coordinate system, x and y, and we have a particle that's rotating around, okay? If we take a point anywhere on the circle, over here, I'm going to do 3 points, okay? And we draw a vector going straight off tangent to the rotation. Okay, these are the velocity vectors and also the acceleration vectors. Not omega and not alpha, but these are tangential velocity. So when we go back and we're talking about the acceleration right here, that is the vector, okay? The angular acceleration is, again, the acceleration of how many rads we are moving or accelerating through a certain distance. So if we're talking about acceleration in terms of if a is equal to alpha r, okay, then this alpha is not a vector. It is actually a line that's traveling around and it's accelerating. It could be constant acceleration, or it can be just changing velocity, or changing acceleration, I'm sorry. But we don't really care about that right now. We just care about constant acceleration. Velocity changes, that's going to create acceleration, of course. The main thing here that these are conversion from translational values to angular values for the three equations. Okay, and that's it on the preview for circular motion in physics and rotation. And then we will go on to some problems later on in the next video. Thank you.
Okay, this is on angular speed, circular motion, and centripetal acceleration, part 1 of chapter 7. So, in uniform circular motion, we want to describe this in physics. We basically are going to be talking about what happens when something is traveling in or rotating in a circle. In this case, we have angular velocity, which is delta theta, is equal to 2 pi. So one revolution of any circle is 2 pi. Or it is 6.28 radians. So the sweep of an angle, delta theta, and delta s. We have an arc length, delta s, and we have the sweep of the angle. And there's a relationship between delta s and delta theta, and that is with r. So what we have is this equation right here, which is the relationship, where one revolution, 2 pi radians, or is 360 degrees. Radians are the units used for circular motion, and revolutions, where 1 rad equals, and we have 1 rad equals 57.3 degrees. So angular velocity is not the same as transitional velocity. So let's define, make sure we understand the difference between angular velocity and transitional velocity, or tangential velocity, it can be also called, is defined as rate of change of an angle over time. So here we have the Greek letter omega. Okay, and what we're looking at here is a angular velocity equation. The omega stands for angular velocity, the change of displacement between initial and final theta divided by that time frame. And what we work with actually is in units, we're going to work with radians per second or rad per second. Usually we would just call it rad per second, and that will be the unit of angular velocity. Also, we can see some problems that will give variables in revolutions per minute, RPM, and basically or revolutions per minute, they're all the same. However, you're going to have to convert those to rads per second to do some of the problems. So let's look at some unit conversions. Example, a tire on a car is moving at 200 RPM. Convert this to rads per second. Okay, so we have our tire traveling at 200 revolutions per minute, RPMs, and we just do dimensional analysis. We have 2 pi rad is in 1 revolution. We have 60 seconds in 1 minute, and then we just go through with the math and we get 20.94 rads per second. It should be noted that when you have something like 200 revolutions or 500 revolutions, if you want to understand if you're going in the right direction when you make your conversions, rads are usually about 10% of revolutions per minute. So this is 20.9, so this is roughly 10% of 200 revolutions per minute. So the next one is convert RPMs in an electric motor shaft rotating at an angular speed of 100 rads per second. So we're going to convert this from rads per second to RPMs. Okay, so we're just going backwards. And so again, we have our 100 rads per second time our dimensional analysis conversions, and we get 955 RPMs. And you can see that again 100 is about 1/10 of the RPM. So let's talk a little more about angular velocity versus linear velocity or tangential speed. Okay, so this is our general tangential speed, where delta S is the arc length. Okay, not the angle, but the arc length, and delta T is the time for that interval. Now, if we have the equation for angular displacement, delta theta is equal to the arc length divided by the radius. Or we can also say that the arc length, delta S, is equal to R times the angular displacement. So let's do a derivation here where we're going to take both of these sides and we're going to divide them by t, okay, and see what we get. Okay, so if we take this equation right here and divide that by t, so I'm taking this part of that equation and we're dividing it by t here. Okay, and so we get delta theta over delta t is equal to omega, and we have r omega. And this, we get this final conversion equation, or this where we convert from linear velocity, tangential velocity, to angular velocity. So if we know the radius and we know the angular velocity, we can convert to tangential or transitional velocity. Okay, and so here, right here is an equation that we can use. If we know the transitional velocity divided by its radius, we can find the angular velocity. So showing that we have the r and we have what tangential velocity is, that it is a velocity that vectors off a tangent. And it could be over in this position over here. It could be here. But in this case, it's constant velocity that is going around, and it would be in meters per second. Okay. Now, if there was an angle right here, then we'd have this angle moving out, and that would be omega. That would be theta, delta theta, over delta t. And the relationship again between tangential velocity and angular velocity is this equation. As r increases, omega decreases as it should. And we see the equation. If r does get bigger, v stays constant, then omega will get smaller. So let's look at an example. We're going to calculate a car moving at 20 meters per second. It gives us a tire radius of 0.25 meters. Calculate the angular velocity. So this is easy. We can just use this equation right here, plug in the values, and we get 80 rads per second. And you should always use radians per second as the default, unless otherwise asked to find RPM, in which case you would convert back to RPMs. How far does a car travel in 10 minutes? So here we have a car that has rotation, it has angular speed, and we're trying to find the displacement, and this displacement is going to be in meters. Note, 1 revolution is equal to 2 pi r. That's just a simple circumference equation, 1.51 meters in this case, for the tire diameter, which is 0.5. So we're going to convert this to RPMs. So we go through our conversion, and this is basically our conversion. The other thing we can do is that we can make a shortcut where we can just take 60 and put it over 2 pi r, and then take the inverse of that to go from RPMs to rads. But to go to rads to RPMs, we can just basically have 60, 2 pi rad, and we get our revolutions per minute. So in 10 minutes, if we are getting 764 revolutions in 1 minute, and don't forget 1 revolution is a displacement of 1.51 meters, then we just take that revolution times what that distance is around the circumference of the rotation, and we are able to get our displacement right here, 1.20 times 4 meters. Okay, we have another example. An 80 centimeter diameter tire rotates at 800 RPM. They want us to find the omega, the angular speed, find the average velocity of the car, and I would assume this average velocity is tangential, and find the distance the car travels in meters in 1 hour. Okay, so let's go ahead. So the first thing that we're going to do is we want to convert this 800 RPM, and we want to convert it to rads per second. Okay, and so this is omega, 83.8 rads per second. This is the angular speed. So we found A. The diameter is 0.8 meters, so the radius is 0.4. So to find the average velocity of the car, or V, we just take omega times the radius. Okay, and we do that here. We have the 83.8 rads per second times the radius, 0.4, and we get the tangential or transitional velocity, if you will, of 33.5 meters per second. And then finally, find the distance the car travels in meters in 1 hour. Okay, so we can use this equation right here, delta x over delta t equals velocity, and this solve for displacement. And when we do, we get our answer of 1.21 times 10 to the 5th meters. Now let's look at acceleration. Angular acceleration. We know that we have tangential velocity is equal to v, is v equal to omega r. If we take that equation up here, this one, and we take and divide both sides by t, we get this equation right here. And we know that omega over t is going to be equal to alpha, where alpha is the angular acceleration in rads per second per second. So we have our tangential acceleration, which is in meters per second, or meters per second square. And then we have our alpha, which is in rads per second squared, times the radius of the circular motion. So let's take a look at some of these angular kinematic equations that actually we're going to take from kinematics when we were doing things in moving in linear paths. We have the equation velocity equals the initial velocity plus acceleration time, and then the angular equivalent would be this equation right here. We know that v is equal to omega r. V sub naught would be equal to omega naught r, and then we'd have what a is equal to alpha r, so we replace it and we get this equation. And then all the r's will cancel out, and we get this as our angular velocity and acceleration equivalent to this equation. Another acceleration equation used is this one right here. And we can do the same thing. We can take each one of these values of v, x, and t, and we can change it by what its equivalent is by using the equations of conversion with radius. And so here the same thing happens. You notice that delta theta r, okay, is now going to be what delta x is, and then we have omega r, that is what v sub naught was, and then we have alpha r, and that's what acceleration in tangential acceleration was equal to. So all these r's of each term will cancel out. And so we have this equation, which is very similar, except for the fact that we're solving for rads here, and it's going to be equal to the initial angular velocity times t, the time, plus 1/2 of the angular acceleration times t squared. And then we have the final equation that we use in kinematics, v squared minus v sub naught squared equals 2 times acceleration delta x. And we just are going to convert the v's, the delta x, and the a's, and we get this equation right here, which is the two angular velocities squared, the difference between them, 2 times alpha, the angular acceleration, times delta theta, the angular displacement. Let's talk a little bit about kinetic energy, how that looks during constant velocity. Basically, we have to replace this v with the square omega r. Okay, and when we do, we get this equation. Sometimes this may come up in some problems, but this would be the equation to find kinetic energy. And we want to make sure that the omega is a constant velocity, angular velocity constant. So let's look at the relations between angular and linear quantities. And these are all three of how we convert from linear to the angular equivalence. Now let's look at another example that's a little more involved. In a machine shop, a grinding wheel is rotating at 700 RPM. The operator shuts off the machine, and it takes 22 seconds for the wheel to stop. So we have a grinding wheel that is moving at an angular velocity, 700 RPM. That is an angular velocity. That is an omega. Okay. The operator shuts off the machine, and it takes 22 seconds for the wheel to stop. Okay. So they want us to find the delta theta. So this is the initial angle and the final angle, the difference, and convert to the number of revolutions the wheel makes before stopping. Okay, then they want us to find the angular acceleration. So in this case, we need to actually solve for the acceleration first. Even though they're asking for it in part B, we need to solve it first. Okay, and so we take the angular acceleration equation, which is omega minus omega naught divided by time. Okay, and we know that the 73.3 rads per second, this has already been converted. This was actually our 700 RPM here. Okay, trying to write with a mouse. Okay, 700 RPM converted, and then we get our answer of our angular acceleration of minus 3.30 rads per second squared. Okay, so we've answered B. Now we'll go back and we'll see if we can answer A. Okay, so in A, it actually does the conversion of showing you how we wound up with 73.3 rads per second. Okay, and this is convert the number of revolutions the wheel makes before stopping. Okay, so we're going to go through, we already did this part right here. We showed that. Now we're going to do how many rads or revolutions it takes, 814 rads. And then we need to convert this to revolutions. So how many revolutions? Well, from that speed, angular speed, to where the grinder was shut off, the wheel turned 130 times before it stopped. And so that is the answer. Let's look at another example. A 20-inch tire is rotating at 1,000 RPM. Again, it's given us the angular omega in RPM. It has an angular acceleration of negative 2.0 rads per second squared. It takes 45 seconds to reach its final velocity. So A, find the angular displacement it makes during the delta t, the time, and find the final velocity. Find the RPMs, and then B, find the linear distance traveled. So this linear distance traveled is going to be in meters. And then the car's velocity at the final velocity. Okay. So we have just a list of what we know. The angular acceleration is negative 2 rads per second squared. Initial angular velocity is 1,000 RPMs. We have a time of 45 seconds. And then we take our 20-inch tire. It has a 0.5 meter diameter if we convert inches to meters. And this works out to an R of 0.25 meters. So first thing to do is let's convert our RPMs to rads per second. Okay, and we do that here, which I've showed you in earlier slides. You can go back and take a look at that. And then we get 106 rads per second. So this is our omega right here. Then A says find delta theta, angular displacement. Okay, there are more than actually 2 equations that you can use to solve this, but we're going to start with one. And you can probably try out other ones if you want. We're going to use this one right here. This is going to be a little easier and simple, more simple to explain. So we plug in the values, okay? We have, this actually should be 6, 105 rads per second times 45 seconds plus 1/2 minus 2, and that's this is the angular acceleration, and this is t. This actually, I think, should be a 6, not a 5. And then we get an answer of this. So this is the how many rads it turned in that period of time, 45 seconds. And then we can convert rads to revolutions by using 1 revolution is equal to 2 pi rads, and we get 437 revolutions. So the wheel turned 437 times completely. And B, find the linear distance traveled in the car's velocity at final velocity. So let's continue with example 7.4. We have our angular displacement, 437 revolutions. So they want us to find the linear distance the car's traveled. So this is going to be something in meters, or it could be in feet, in the car's velocity at final velocity. So let's take a look at this. So we're going to use this equation right here, how to convert displacement. And we have our radius, we have our theta, and we get 686 meters. So that is our displacement. Then we need to find the final velocity. Initial angular velocity is 105 rads per second. So we're going to use this equation right here. It would be the right one to use because we're trying to find the final velocity. Okay. And so we have the initial in here, we plug everything in, and we get 16 rads per second. And that is our final velocity. Now if you remember, in this case we were at 105 and then we were deaccelerating angular velocity, angular acceleration, excuse me, and we should have a lower rad per second. Omega. We do 16.0 rads per second. And let's convert that to meters per second. by using this equation right here, and we get 4.00 meters per second. Okay, so that answers that part B. Okay, let's move on. Subject in circular motion, centripetal acceleration. Okay, centripetal acceleration is the inward acceleration from the outer circle of travel, not to be confused with centrifugal acceleration or centrifugal force. As in physics, basically, centrifugal force is a myth. Okay, it's not what's really happening. So what they're saying basically is, as something is rotating in a circle, it has this centripetal acceleration right here that is going vectoring towards the center of rotation. So when a mass travels, and this is important, in a curved or circular motion, it is in a non-inertia frame of reference, meaning that there's an acceleration. Okay, and that acceleration is the centripetal acceleration, meaning the mass itself has an acceleration acting on it. Remember Newton's first law. A body wants to stay at rest or constant motion and or resist changing direction. And so if you have a mass that is going around here at a certain speed, it is constantly changing direction. So it is in a non-inertial frame of reference. So let's take a good example of this. We're looking down at a dashboard right here, and there is a sunglass case on the dashboard. And we are looking down on a car. We look down here. Here is the car over here, moving through a curve in a road, and it's showing, the arrows are showing its centripetal acceleration towards the center. And we're going to look at what's happening to the sunglass case right over here. And we're going to see through each frame. This would be frame 1, this would be frame 2, this would be frame 3, and so on. And what happens to the sunglass case? There's no friction between the dashboard and the bottom of the case. So let's take a look as we go through each frame. So now in frame 2, as the car is now starting to go through the curve, the sunglass case now has displaced. Okay. And we find that now it's getting closer to the center of the dashboard, where over here in the initial frame it was on the left side of the dashboard. This frame shows now it is at the center of the dashboard, and finally it's over here near the other side, the right side of the dashboard. It has actually transitioned from the left to the right. Okay. But the force has always been, and the acceleration has always been towards the center. The reason why it stays straight is because it's a mass. It has no friction that's going to stop it from moving. It wants to stay moving at a constant speed, and it doesn't want to change its direction. However, when the sunglass case does reach this part of the dash, it's going to hit the window or whatever object there is by the dashboard, and it can no longer move any further. Thus, this is where you have, like in test tubes, where you have heavier materials that have more inertia. Go to the bottom of a test tube in a centrifuge that separate different layers, where the heavier layers would be here in this area right here, and the lighter ones would be the same over here somewhere. Okay, so it basically helps distribute the densities of things, and simply it's done by inertia and centripetal acceleration. Okay. So let's look at what the derivation of a centripetal force and acceleration equation is. Okay, so we have a circle and we have a triangle. This is an equilateral triangle, and if we sit there and we label each side of this triangle with R, R, and R, okay, that is the length, and then we have the arc from that point to this point that we call delta S. So we have a ratio. That ratio is delta S over S. And we're going to do the same thing, but we're going to change from R to V, denoting velocity. Okay. And so if this is true in this case, this must be true too. So we have then this expression where delta V divided by V equals delta S divided by S. It's basically just a ratio comparison. So let's solve now for delta V in this case. And then let's take and divide by delta T on both sides of the equation. Okay. So here we have divided by T. We've solved here, we did the first step and solve for delta V, divide both sides by delta T. Okay, and then we know that delta V over delta T is acceleration. Okay, and so we get this expression here. And then finally, we have this expression, which is the acceleration of centripetal force. I'm sorry, centripetal acceleration. The velocity speed, that would be the tangential velocity going around in a circle, divided by its radius. And you'll be able to calculate the centripetal acceleration. We can also do it with rads per second too, but we first have to square it and then take that times the radius. So this is our centripetal acceleration equation. We can also have a force. It's always pointing to the center of the rotation. And if we apply Newton's second law, we can determine centripetal force on a mass moving at a constant tangential velocity. So when we do have some mass that is traveling around, we will have a force, a centripetal force. And that's centripetal force will be towards the center. So basically by taking Newton's second law and by taking the substituting the A for the centripetal acceleration, we have this equation right here. And so this equation is our centripetal force equation. So it happens when there is a mass of some type, of some quantity that is rotating around in a circle, and this force is towards the center. So let's look at a problem. A NASA engineer wants to design a space station like a giant wheel in space. When it rotates at a certain velocity, it will create a centripetal force upward to simulate gravity. If he calculates a space station can take a velocity, a load of 25 meters per second, what is the overall diameter of the space station? So basically, we can use the acceleration, centripetal acceleration equation, because we can take this acceleration, we know what we're looking for. We're looking for G, 9.8 meters per second squared, to simulate gravity in the space station. Okay, so if that's the case, then we can take this equation right here and solve for R. And that's what we did right here. We solve for R. We have our velocity, which is what is rated at 25.0 meters per second. We square it, divided by the acceleration of gravity, because that is the acceleration we want. and we get the radius of what the spaceship should be, 63.8 meters. Or the diameter, double that, 128 meters as it's rotating. Let's look at another example. We have a 20 meter in diameter Ferris wheel type, which is rotating at 15 RPMs vertically. Find the force on the 100 kilogram person at the very top. So we want to find the centrifugal force at the top and the bottom. B, find the forces on the rider when the wheel is at the 3 o'clock position, 90 degrees magnitude and direction. So what we're looking at right here is that when the rider is right about there, what are the forces acting on that? So let's first convert RPMs. So we convert 15 RPMs, that is 1.57 rads per second. Find the force at the bottom. First, the centrifugal force is this equation here. Now, if you remember from last time, we had omega squared r. This is diameter, divided by 2 is this r. So we have our mass times omega 2r. Okay, and this is going to be equal to the centripetal force. Okay, so let's take what's happening here. On the bottom right here, we have the force due to gravity plus the force due to centripetal force. Okay, so the gravity is going to be negative right here, and centripetal force will be positive. So basically we're summating all the forces acting on at the bottom. And then we just take this and we use algebra and we get this equation, plug in the values, and we find the force at the bottom is 1,490 newtons. And the centripetal acceleration is 14.8 meters per second squared. And that is about 1.52 Gs. If you take 9.8 divided into 14.8, you get 1.52 Gs. Let's find the force at the top. So we do the same thing. Plug the values in, and we find it is a negative 3,450 newtons downward. So it's basically just doing the same thing. The acceleration is going to be equal to minus 34.5 meters per second squared. And T here is, even though it is standing for the top position, that's about 3.51 G. So at the top, the rider is going to experience more G's. And these G's will be in the forms of a negative 34.5 meters per second squared. But what happens is the rider, because of inertia, is going to feel like he's flying off his seat. So when he's at the top, that's a round part, he's going to feel going this way because the acceleration, the negative acceleration, is downward. So the inertia is going to send him up. Now let's try to figure out this one right here where the rider is at the 3 o'clock position. First of all, we have vectors. We have f of g, that's going to be like our y vector down, and f of c is going to be our x vector. And so we can easily find our resultant force vector. So let's find the centripetal force. And let's find Fg. So our centripetal force, this is the x vector, this is the y vector. Okay, and then we have two of them now. Okay, and then we find the magnitude. Plug in the numbers, and we get f of r, which is the resultant vector. Now this is, the rider was going to be feeling, or this force is going to be on the Ferris wheel. towards this direction, not towards the center actually now, but it's actually going to be over here because of gravity interfering with the other centrifugal force. Okay, and then we can find the angle, and that's 68.4. That would be 68.4 down this way. Okay. So that's about, as I said before, negative 3.51 Gs there too. Okay. I'm sorry, this is negative 3.51 Gs at the top, 1.52 Gs at the bottom. Let's look at another example. A car is moving on a curve at a constant speed of 45 miles per hour on a level circular curve of radius 70 meters. What minimum coefficient of static friction between the rubber tires and the pavement is required to keep the tires from sliding off the road? So as this car approaches this curve, its inertia is going to want to move the car this way. Okay, the only thing that's going to stop that is the friction. Okay, then the other force is going to be this centripetal force, which wants to pull it towards the center of the curve. Okay. So let's first convert 45 miles an hour, and then we get our 20.1 meters per second. Our FSC, this is centripetal force, has to be equal to the frictional force maximum for the car to stay on the road. So the coefficient of friction, static friction, in this case, it has to be between cement or whatever the material of the road is and the tires. Okay, so this is basically now, this equation has to be telling us that the net force has to be 0. Okay, so we have this equation. This is what? This is centripetal force, and this is the friction. They must be equal. And so now we're going to solve for mu, the coefficient of friction, static, and we just plug in the values, and we get 0.589. That is our mu value that the coefficient of friction between the tires and the road has to be, and to enable the car to travel at a constant speed of 45 miles per hour on a level circular curve of a radius of 70 meters. So let's look at another problem. Engineer is designing a road with a curve in it. A car must take this curve at 70 miles an hour. The specification of the tire indicates coefficient of friction is equal to 0.555. Find the radius of the curve. So this is similar to the last problem, but they want us to find the radius. Okay. So again, we need to convert the 70 miles an hour to 31.3 meters per second. And then we have our equation that we derived in the last slide. And we need to solve for V. I'm sorry, we need to solve for R. Okay, we need to solve for R, and here we solve for R. And so that radius of the curve has to be 180 meters. Okay, that ends part 1 on circular motion, chapter 7. We will have part 2, which will be on gravitation and Kepler's laws. Thank you.